A secured face recognition system using principal component analysis and hybrid cryptography. Abstract face recognition is used for real-time application. So reliability is the more important matter for security. Facial recognition is rapidly becoming area of interest. Face biometrics is useful for authentication that recognizes face. This paper represents secured face recognition methods and discusses their advantages. The purpose of this paper is to provide secured face recognition methods. Principal component analysis is used for face recognition and cryptography is used to secure the face image. Introduction. A system requires reliability to recognition the identity of an individual entity. The purpose is to ensure that the services are accessed only by an authorized user and not else others. In biometric, face recognition is based on their physiological and/or behavioral characteristics of individuals. A biometric recognition system consists of 4 main modules: I. Image captures of a biometric trait. 2. Feature extraction module that extracts certain features from the biometric data. 3. System database that stores the features extracted from biometric data. 4. Matcher module that matches the features extracted from the biometric imputed data with the features stored in the system database. Face recognition methods. Face recognition methods divided into categories: I. Knowledge-based methods. I. Feature invariant methods. 2. Template matching methods. I. Appearance-based methods. Knowledge-based methods are encoding our knowledge of human faces. These are rule-based methods. They try to capture our knowledge of faces, and translate them into a set of rules. It's easy to guess some simple rules. For example, a face usually has 2 symmetric eyes, and the eye area is darker than the cheeks. Facial features could be the distance between eyes or the color intensity difference between the eye area and the lower zone. The big problem with these methods is the difficulty in building an appropriate set of rules. There could be many false positives if the rules were too general. On the other hand, there could be many false negatives if the rules were too detailed. A solution is to build hierarchical knowledge-based methods to overcome these problems. These methods show themselves efficient with simple inputs. But, what happens if a man is wearing glasses? There are other features that can deal with that problem. For example, there are algorithms that detect face-like textures or the color of human skin. Feature invariant methods that try to find invariant features of a face despite its angle or position. Facial recognition utilizes distinctive features of the face including distinct microelements like mouth, nose, eye, cheekbones, chin, lips, forehead, ears, upper outlines of the eye sockets, the area surrounding the cheekbones, the sides of the mouth, and the location of the nose and eyes. The distance between the eyes, the length of the nose and the angle of the jaw. These algorithms compare input images with stored patterns of faces or features. Template matching methods try to define a face as a function. One can try to find a standard template of all the faces. Different features can be defined independently. For example, a face can be divided into eyes, face contour, nose, and mouth. Also, a face model can be built by edges. But these methods are limited to faces that are frontal. A face can also be represented as a shape. Other templates use the relation between face regions in terms of brightness and darkness. These standard patterns are compared to the input images to detect faces. This approach is simple to implement, but it's insufficient for face detection. It cannot achieve good results with variations in pose, scale, and shape. However, deformable templates have been proposed to deal with these problems. A template matching method whose pattern database is learned from a set of training images. In general, appearance-based methods rely on techniques from statistical analysis and machine learning to find the relevant characteristics of face images. PCA algorithm principal component analysis, PCA, is well-organized method for face recognition 1. It is one of the most usable methods for a face image. It is used to reduce the dimensionality of the image and also holds some of the variations in the image data too. It is projecting face image data into a feature space that covers the significant variations among known facial images. Those significant features are known as eigenfaces, because they are the eigenvectors or principal component of the set of faces. That is not necessary to correspond to the features such as eyes, ears, and noses. The projection operation characterizes an individual face by a weighted sum of the eigenfaces features. So to recognize a particular face, it is necessary only to compare these weights to those individuals. The eigenobject recognizer class applies PCA on each image, the results of which will be an array of eigenvalues. To perform PCA, several steps are undertaken. Principal component analysis, PCA. Principal component analysis, PCA, is a simple yet powerful technique used for dimensionality reduction. Through it, we can directly decrease the number of feature variables, thereby narrowing down the important features and saving on computations. From a high-level view, PCA has three main steps. Compute the covariance matrix of the data. Compute the eigenvalues and vectors of this covariance matrix. Use the eigenvalues and vectors to select only the most important feature vectors and then transform your data onto those vectors for reduced dimensionality. The entire process is illustrated in the figure above, where the data has been converted from a three-dimensional space of 1000 points to a two-dimensional space of 100 points. That's a 10x saving on computation. Computing the covariance matrix. PCA yields a feature subspace that maximizes the variance along the feature vectors. Therefore, in order to properly measure the variance of those feature vectors, they must be properly balanced. To accomplish this, we first normalize our data to have zero mean and unit variance such that each feature will be weighted equally in our calculations. Assuming that our dataset is called X, the covariance of two variables measures how correlated they are. If the two variables have a positive covariance, then when variable increases so does the other. With a negative covariance, the values of the feature variables will change in opposite directions. The covariance matrix is then just an array where each value specifies the covariance between two feature variables based on the xy position in the matrix. Where the x with the line on top is a vector of mean values for each feature of x. Notice that when we multiply a transposed matrix by the original one, we end up multiplying each of the features for each data point together. Computing eigenvalues and vectors. The eigenvectors, principal components, of our covariance matrix represent the vector directions of the new feature space, and the eigenvalues represent the magnitudes of those vectors. 6. Since we are looking at our covariance matrix, the eigenvalues quantify the contributing variance of each vector. If an eigenvector has a corresponding eigenvalue of high magnitude, it means that our data has high variance along that vector in feature space. Thus, this vector holds a lot information about our data, since any movement along that vector causes large variance. On the other hand, vectors with small eigenvalues have low variance, and thus our data does not vary greatly when moving along that vector. Since nothing changes when moving along that particular feature vector I.E, changing the value of that feature vector does not greatly affect our data, then we can say that this feature isn't very important and we can afford to remove it. That's the whole essence of eigenvalues and vectors within PCA. Find the vectors that are the most important in representing our data and discard the rest. Computing the eigenvectors and values of our covariance matrix is an easy one-liner in NumPy. After that, sort the eigenvectors in descending order based on their eigenvalues. Projection onto new vectors. At this point we have a list of eigenvectors sorted in order of importance to our dataset based on their eigenvalues. Now what we want to do is select the most important feature vectors that we need and discard the rest. We can do this in a clever way by looking at the explained variance percentage of the vectors. This percentage quantifies how much information, variance, can be attributed to each of the principal components out of the total 100%. Let's take an example to illustrate. Say we have a dataset which originally has 10 feature vectors. After computing the covariance matrix, we discover that the eigenvalues are 12, 10, 8, 7, 5, 1, 0.1, 0.03, 0.005, 0.0009. The total sum of this array is equals 43.1359. But the first 6 values represent 42/43.1359 equals 99.68% of the total. That means that our first 5 eigenvectors effectively hold 99.68% of the variance or information about our dataset. We can thus discard the last 4 feature vectors as they only contain 0.32% of the information, a worthy sacrifice for saving on 40% of the computations. Therefore, we can simply define a threshold upon which we can decide whether to keep or discard each feature vector. In the code below, we simply count the number of feature vectors we would like to keep based on a selected threshold of 97%. The final step is to actually project our data onto the vectors we decided to keep. We do this by building a projection matrix. That's just a fancy word for a matrix we will multiply by to project our data onto the new vectors. To create it, we simply concatenate all of the eigenvectors we decided to keep. Our final step is to simply take the dot product between our original data and our projection matrix. Secured Face Recognition System. The Principal Component Analysis, PCA, is the most successful techniques that have been used in face recognition. PCA is a statistical method under the broad title of factor analysis. The purpose of PCA is to reduce the large dimensionality of the data space observed variables to the smaller intrinsic dimensionality of feature space, independent variables, which are needed to describe the data economically. 3. This is the case when there is a strong correlation between observed variables. When there are different scales used for the measurement of the values of the features, then it is advisable to do the standardization to bring all the feature spaces with mean equals 0 and variance equals 1. The reason why standardization is very much needed before performing PCA is that PCA is very sensitive to variances. Meaning, if there are large differences between the scales, ranges, of the features, then those with larger scales will dominate over those with the small scales. For example, a feature that ranges between 0 to 100 will dominate over a feature that ranges between 0 to 1, and it will lead to biased results. So, transforming the data to the same scales will prevent this problem. 5. That is where we use standardization to bring the features with mean value 0 and variance 1. So here is the formula to calculate the standardized value of features. To calculate a matrix that summarizes how our variables all relate to one another, then break this matrix down into 2 separate components, direction and magnitude, then can understand the directions of our data and its magnitude, or how important each direction is. The red direction and the green direction. In this case, the red direction is the more important one. It's given how the dots are arranged 6, 7. By identifying which directions are most important, compress or project the data into a smaller space by dropping the directions that are the least important. By projecting data into a smaller space, we're reducing the dimensionality of feature space, but because we've transformed data in these different directions, to made sure to keep all original variables in it. Every crypto system, which has a finite number of keys, can usually be analyzed by key trial, deciphering the ciphertext with all possible keys until some recognizable text appears. 8. In many classical cryptographic systems, the testing of keys could be performed by hand. The stimulus for the development of computers was the need to be able to test large sets of possible keys to decipher coded traffic. Modern crypto systems are such that the number of possible keys is generally so large as to make exhaustive key trial infeasible. 9. Even computers are limited, and some analysis must precede key testing for the process to be successful. A mixture crypto system is a show which uses different figures of different sorts together, each to facilitate its best potential advantage. One general approach is to make a discretionary puzzle key for a symmetric figure, and a short time later scramble this key by methods for an uneven figure using the recipient's open key. The information itself is then encoded using the symmetric figure and the puzzle key. Both the mixed riddle key and the encoded information are then sent to the recipient. The recipient translates the riddle key first, using his/her own private key, and a while later uses that key to unscramble the data. 10. Conclusion. This paper presents a secured face recognition system. Principal component analysis is used for face recognition, and in cryptography hybrid is used to secure the face image. Face recognition using PCA method has a very good and fast ability to recognize human face. PCA is used to reduce the large dimensionality of the data space observed variables to the smaller intrinsic dimensionality of feature space independent variables. Hybrid encryption is a mode of encryption that merges two or more encryption systems. It incorporates a combination of asymmetric and symmetric encryption to benefit from the strengths of each form of encryption. These strengths are respectively defined as speed and security. No more time fraud. One of the big benefits of using this system in company to protect from time fraud. It will be impossible for unauthorized user punching to occur, since everyone has to have their face scanned to clock in. Not only can you track employees, but any visitors can be added to the system and tracked throughout the area too. Anyone that is not in the system will not be given access. Automated system. Many companies like the fact that biometric imaging systems are automated. You won't have to worry about having someone there to monitor the system. Easy integration. This face recognition system are secured to integrate to companies, hospitals to make authorizes users, patients, get access in hospitals and know their health status, and in banking sector etc.